Plasmonic nanomaterials are a special type of material which can have strong interaction with incident light, and this interaction is largely dependent on the shape of the materials. Therefore, for decades, various types of plasmonic nanostructures have been studied and exploited for different applications, ranging from biosensing, enhanced solar cell, light manipulation, and so on. Particularly in this work, we are focusing on a dimer structure where two plasmonic nanoparticles are brought close to each other with a gap size only less than 10 nanometers. We have developed a method which can make these dimer structures scalable on wafer scale and even potentially for real production. The nanometer size gap between two plasmonic nanoparticles are very useful. They are so-called hotspots, because when incident light hits the dimer structure, its electromagnetic energy will be concentrated in this gap region, leading to a dramatically enhanced electric field. And when a molecule is trapped in this gap region, its Raman signal will be increased by orders of magnitude, knocking down its detection limit to single molecule level. Here, we use a combination of nano-imprint lithography and shadow evaporation to pattern the dimers. Nano-imprint lithography is used to pattern wafer-scale holes inside the polymer layer. Then, a two-step deposition is used, where each step of deposition will form one part of the dimer. The deposition directions of the two steps are opposite to each other, and they all have an angle with respect to the normal direction to the substrate. By tuning the deposition angles properly, we can consistently form sub-10-nm gaps throughout the wafer. In one example, dimers are fabricated on 15-nm thin silicon nitride membrane, in which we can visualize these dimers under the transmission electron microscope. We can further probe the plasmonic modes of these dimers by passing through an electron beam, where the electron energy loss will be recorded by a spectrometer, and each peak on the spectrum will be directly related to a plasmonic mode of the dimer.
The nanostructures fabricated by the group of Professor Wang at Stanford University exhibit extremely small gap-to-size ratio. From a computational point of view, this can become extremely challenging. First, in electrodynamics calculations, one requires to spatially discretize a large nanostructure volume with very small unit cells to account for sub-10 nanometers gaps, which can drastically increase the computational cost. Second, the very small gap-to-size ratio leads to very strong hybridization or coupling between the two metallic nanoparticles forming the dimer. This leads to very complex physics. So because of this complexity of the fabricated nanostructures, in particular the actual geometry and dimensions, as I just mentioned, no traditional electrodynamic method available could be used for this particular case. To tackle these challenges, we had to develop and use novel theoretical and computational approaches. First, we used an advanced and sophisticated analytical theory called plasmon hybridization theory that was developed in 2003 in a group of Professor Norlander at Rice University. A second approach was to use a state-of-the-art computational method that we recently developed and implemented at Rice University for the calculation of electron energy loss spectroscopy, or EELS. This was developed to implement this method, this calculation, in finite-difference time domain method, FDTD. So the agreement between experimental results and theory was surprisingly very good, given the complexity of the nanostructures. In the end, the theory really nicely highlighted the complex plasmonic properties of these sub-10 nanometers dimers, opening the way to future and more fundamental studies on similar model systems.